Welcome everybody to Sustainable River Basin Management, Module 2, Part 3. Today we will be talking about water balances or water budgets. Let's first of all come back to our most relevant physical laws in hydrology. We touched upon the importance of physical laws when we spoke about hydrological models in our previous class. The important laws that you should be aware of and you should have ready in your head are conservation of mass, Newton's law of motion, the laws of thermodynamics, and Fick's first law of diffusion. We'll come back to one or the other throughout the classes. Now let's start with today talking about water balance. Let's talk about the conservation of mass. In very brief, it states the amount that goes in minus the amount that leaves the system equals the change in storage. Now this can be expressed in a mathematical form, and I is inflow, Q our outflow, and delta is our change in storage. And this has to be observed as a changing state. So it has to be integrated over time, and we can express it in this way. And again, we have to resolve this for each of the time steps that when we monitor a system, it changes constantly. Now, this is fairly simply looking equation is a very important one because it actually is our global water balance equation. Now, the second, which is important for today's class, is the conservation of energy. Essentially, it starts from the same, the amount of energy minus incoming minus the amount of energy going out of our system equals the change in storage. And this can be put into a mathematical relationship again, where we express our downward or inward radiation change over time minus the outgoing radiation over time plus the change or plus minus the latent heat flux and sensible heat flux equals the change in heat storage or change in temperature. That heat storage could be, for instance, the soil layer or a water body. And this relationship is extremely important for the calculation or to obtain evaporation data, unless we try to measure evaporation. Now, talking about water balance or water budget, let's define what we mean by this. Essentially, we are able to express in the form of the water balance, the amount of water that is available in a particular area. And that availability essentially is based on hydrological or climate data and physiographical background. So means we will be talking about water availability in our next lecture, where we will use a slightly different definition for water availability. Now, when we talk about water availability in our water budget, that is merely based on hydrological and climate data and physiographical backgrounds of our catchment. So that balance can be used at a global, national, watershed, urban scale. We can come up with a water balance at any required geographical and temporal scale. And what do we need this for? It essentially serves for strategic planning of water resources, for socioeconomic potentials of region, to determine priorities. Should we go for tourism, for instance, in a particular area, or rather produce cash crops in a particular area? It could be used for to come up with budgets for local water utilization and others. So it's a very basic and very important component of water management. How do we come to a water balance in a catchment? Let's just use a box model, a catchment, any type of catchment, and our basic input components, precipitation and groundwater inflows into our catchment. And our outgoing components, our evapotranspiration, and our runoff in the form of surface runoff or in the form of subsurface groundwater outflows. And then within our catchment, our storage changes. Now, brought into a catchment level water budget, this equation will look like this. The sum of incoming minus the sum of outgoing amounts equals the change in storage. So what we mean by precipitation, it summarizes liquid and solid. So we have to measure both liquid and solid. If this is applicable, groundwater in the form of liquid we're speaking of. The stream outflows, we speak of rivers. The evapotranspiration, we speak of water vapor. The groundwater outflows as a liquid again. The change in storage, and we refer to any form of storages in the form of liquid or solid state, and this would entail our reservoirs, our wetlands, and our aquifer systems. So this gives us already an idea of how quickly it becomes very complex to express, to measure, to observe the variables that we need to calculate our water balance. Now, let's talk about the inputs to the water budget. I'm not going to discuss the details of how to measure each of those. You should read about this, you should have that information as a working knowledge, but we are not talking about this in our class. Just an overview, precipitation and stream flow are routine measurements, as you may be aware of. In many areas, it's reported in either millimeter per time or cubic meters per second for a particular catchment area. So we need to know what our catchment area is. Evapotranspiration is measured in some places, in very few places only. In also very few places, just evaporation is measured, potential evaporation is measured. It can be estimated from meteorological data, from climate data, based on the law that we introduced in this class. It may be reported also in a wide range of units, which could be watts per square meter, it could be in millimeters per time, and again, it has to be based upon a particular area, a catchment area or sub-catchment area. So keeping all this already in mind, we have to work in single units if we want to come up with a water budget, which could already in itself be a challenge because it's been reported and recorded in so many different units. Another important input component is the change in storage, which is not been routinely reported, but can be estimated. So, for instance, through measurements of lake levels, changes in lake levels, the measurement of soil moisture, measurement of water well levels, and you can already see how that where as an additional challenge comes that we measure only in one point, whereas we have to relate the storage to an area, our catchment area, and a very important yet other input to our water budgets are groundwater flows, inflows and outflows, and those are equally measured only in very, very few places. In some we can measure it directly, in springs for instance, where we have direct access, a window to our groundwater, or in boreholes again, it's just a point measurement, whereas we need to relate this to our catchment as an area. And we could, in most of the cases, we just calculate it from, for instance, tracer studies or from flow models. And that's a major missing piece in many of the water budgets because it's not being reported regularly or routinely, and it again may be measured in various units which not facilitate the calculation in one and the same water budget. So what we want to make clear here is that the calculation of a complete water budget is not at all a simple exercise. It is never simple, and it requires a lot of data. And filling those data gaps usually require a significant investment in measurement, which means having equipment available, having a monitoring network in place, and possibilities to collect those data and analyze those data in the needed frequency. Sometimes a partially existing water budget can be used to estimate or calculate unmeasured flows, for instance, groundwater or evapotranspiration. But that is only sometimes, and I would like to point you to this example here from the literature, which you can later also access from our portal, where this exercise of putting different sources together, all this has been nicely demonstrated and how difficult it becomes to come up with a proper water budget. Another very basic relationship that you should know and be able to handle at any time is the relationship between height per time, as we very often measure rainfall in our rain gauges, to a volume per area per time unit, where we then come up with budgets at a catchment scale or sub-catchment scale. Now, there are ways of working with simplified versions of the water budget, which I want to briefly demonstrate here in this case. In the case of the evapotranspiration, which is very often the missing part, one of the missing parts. So when we work with a long-term record, and this is the emphasis here, we can simplify. We can assume that the long-term differences between groundwater inputs on this side, and which means inflows and recharge of groundwater, and the groundwater outflows, the groundwater discharge, may not vary much. They are small. And for that reason, we may assume that our groundwater inputs and groundwater outputs become zero. In that case, we can simplify our water budget equation to the one lined out here below. Now, the next step on this would be the difficulty on storage change to estimate or determine this. And again, we know that at very short term, the changes in our storage are quite big and quite essential. Just think of the beginning of a growing season and the end of a growing season, or the situation of our water storage before the rainy season and after the rainy season. You see that the change in storage is very relevant and very large. However, if we take long-term records over and compare always periods, same periods, for instance, hydrological years, then the net change in storage becomes fairly small. And in such cases, we can set our change in storage to zero, only in such cases. And then we can simplify our water balance equation to this version, which helps us to calculate ET or come up with a regional long-term balance, which can help us analyze our water situation already to quite an interesting and elaborate point. We will come back to this equation at a later stage. Now, I want to show you a few examples of water budgets to give you an idea of how this looks like and how it's been applied. First example is our various river basins in the US. A source of information is here. And what we have in this table is rainfall, we have discharge, and then we have a relationship, a P, precipitation minus discharge for each of these river basins, and we have a ratio. This ratio is or can be characteristic for river basin, for climate, specific climate conditions, for specific geographical regions, geological conditions, and for that reason can give a very quick first overview of what the water budget situation is over a large area, like a country. So this is one example, and which gives us already an idea of where we have difficulties in water supply probably, and limitations. And we also can see how much of the water, that is rainfall, transforms actually into available discharge, into water that can be abstracted and maybe used or is available for biological activity. Another example that I want to show here is that the importance, very often and ever becoming more important, to factor in interbasin transfers and to conduct projections of water availability. Now, this is an example from South Africa, the Oliphant River catchment, and we have data sets from the year 2000 and a prediction for 2025. What summarized here as a water budget is the reliable water reserves, the interbasin transfer taking place into the Oliphant River, and the basin transfers that take place out of the Oliphant River catchment, what the requirements are in terms of water, which means that is a human factor, how much water is needed for all of the different usages, and how much water is actually available. And what we see here is that already in the year 2000, summing our reliable local reserves and our interbasin transfers minus our transfers out of the basin, we already see that we have a negative balance here. So that is a very important information for planning purposes when our water balance is negative. And this does not become better for the future projection. So this is already a useful management information based on which planning and strategic decisions can be taken. Another example where physical availability and utilization are brought together, a water budget again, in this case from India, and India-wide, not based on a catchment, but based on what the country as such has available. We can already here see what is available or existing today, what has been used for the different purposes, agriculture, industry, domestic, municipality, and what the projections are for the year 2030. And we can see that this is growing, the demand is growing, but our available existing water resources will not grow if we only look into what is available within India itself, and that there will be a water deficit that has to be covered already very soon. Now, as a last example, a very important part also, the transboundary water balance. We have looked at India as a case, as a country water balance, and now a transboundary water balance. We have our water resources here, and then the different components. The water resources available in two countries in the Asian region, which and the amount that has been passed on to the country of interest. So the sum of the two water resource columns here would be the amount of water available in this country. Then we have this blue flow indicating that an amount of this water has been passed on across the border to another 3 countries and been used there, and eventually been discharged into the Aral Sea. And then within this country, there are different usages, consumptive usages of this water. For withdrawal, there's a water loss and water use, which have to be deducted from this amount. And we have a wastewater discharge out of this, which again joins the transboundary flow towards the Aral Sea. So that is a very efficient way also of analyzing regional water budgets, and also efficient ways to communicate and prepare also negotiations between those countries sharing water resources. Now let's conclude here. A complete water budget requires accounting for a number of elements. First of all, we have to start from solid climate and hydrological data, and this is the first point or stepping point where the difficulties start. Hydrological data may not be available at the scale that we require, at the frequency that we require. The consistency may not be there. We may not be able to have the same consistency across the entire catchment if the catchment is being shared by various countries, for instance. This is the starting point. And then we need to budget into or account for the ecosystems requirements of our, in terms of water use, water utilization, and we have to factor in our human interventions, our human utilization, which means our withdrawals, our transfers into our catchment, out of our catchment, the discharges, and the consumptive uses of water. All of this make up our water budget, far beyond the hydrological models that we have been talking about in our previous class. And at this point, I want to stop, and next time we will be talking about water availability, following up on our water budget discussion today.